So when your variables all vanish, it means that the number of solutions that the equation has is not usual. Most equations, most linear equations, let's say, have the property that they have only a single solution. And by solving for the variable, by unwrapping the variable, you discover what that solution is. But it's not always the case. It's 99.99% of the time the case. But there are cases where you have linear equations that don't just have one solution, that they might have no solution at all, or better yet, they might have all real numbers as solutions. So let's take a look at what to expect when that happens. So again, most of the time, this doesn't happen. Most of the time, linear equations have a single solution, one and only one solution. And so the difficult thing is when the variable disappears, when you suddenly find yourself with no x's or no w's or whatever as part of your equation, it's difficult to know how to interpret that the first time it happens. So let's take a look at how to interpret that. If the variable in an equation disappears, what happens is that that variable's value loses the ability to affect whether the equation is true or false. Therefore, when the variable disappears, it means that the original equation is either always true, in other words, always balanced regardless of what value that variable had, or it's always false, in other words, always imbalanced regardless of what value the variable originally had. So we're going to end up with an equation which was either always true from the beginning, or which was never true from the beginning. So our strategy is not going to be any different. We're not going to be able to tell ahead of time that this is going to happen. So we're going to approach solving this linear equation the way that we usually do. Both of our examples here have variables on both sides, so we have to contend with that first. Let's think about getting all the variables onto one side of the equation, always by subtracting. Once the variables are all on one side, we'll be able to reverse the order of operations to unwrap the arithmetic that surrounds it and get the variable by itself. And then, if the variable happens to have disappeared, you're going to be left with an equation that has only numbers in it. If that equation is actually balanced, if it's true, it means that all real numbers must have been solutions to the original equation. If the equation that you get there is false, if it's imbalanced, that means that the original equation is also fundamentally imbalanced and that there is no value of the variable which solves the original equation. So when your variable disappears, you either have a situation where there is no solution to the equation, or a solution where every possible value for the variable is a solution. Let's look at what happens in part A. Let's solve this equation, again, by first of all thinking about getting all variables to one side. But before we even do that, let's simplify. We've got an expression on the left-hand side that has some parentheses in it. I've got an expression on the right-hand side that has some parentheses in it. So before we do anything else, let's deal with that. Let's get around the order of operations here by distributing the multiplication outside those parentheses across the addition and subtraction that's on the inside. If I do that, then on my left-hand side, I'll get 3w minus 6 when I distribute. On the right-hand side, negative 2w minus 6. Then to finish simplifying, I've got a pair of like terms, 3w and minus 5w on the left-hand side, which when I combine by subtracting those coefficients, 3 minus 5, I'll get negative 2w. So after all the simplifying happens on the left and right-hand side of this equation, I get an equation which says negative 2w minus 6 is equal to negative 2w minus 6. And already, if you're looking at this equation, your sort of antenna is going up and saying, well, this is weird. I have an expression on the left-hand side, expression on the right-hand side, which are now quite obviously identical to one another. So what's going to happen? Well, rather than worrying about that, let's just go back to our strategy. Let's get all variables to one side of this equation. Again, always by subtracting. So I'm going to maybe focus on that negative 2w that's on the right-hand side of this equation and try moving it to the left by subtracting negative 2w. That's the same, of course, as adding positive 2w. And when I do it, not only do my w's from the right-hand side go away, negative 2w plus 2w is going to give me 0w, otherwise known as 0. But the same thing happens on the left-hand side also. Negative 2w plus 2w is 0. And when the dust settles, the only things left on the left and right-hand side of this equation are constants. Negative 6 is equal to negative 6. So my w's are gone. They've vanished. And therefore, again, w has lost the ability to affect whether this equation is true or false. which means that because this equation here at the bottom is completely independent of the value of w, that means that the equation in the beginning, because it's equivalent to it, must also be completely independent of the value of w. It's either always true or it's always false. And looking at the equation at the bottom here, -6 equals -6, because it's always true, it's obvious that -6 is equal to -6 now. That must mean that our original equation must also always be true, regardless what value w takes. So all real values of w satisfy the original equation, because all real values of w satisfy this identity that we derived at the end. Identity, by the way, is the name that we give to this phenomenon, right? That we started with an equation that had variables in it, but whose truth value was always true regardless of the value that that variable took. So how do we respond to this question? We're going to choose the option that says all real numbers are solutions. So here was an example where the variable disappeared, and when the variable disappeared, we were left with something which is always true. In this example, -6 equals -6, always true. Therefore, since that equation is always true, the original equation is always true as well, and all real numbers are solutions. Let's see what happens in part B. Same strategy, maybe a different result, we'll see. So in this equation, we want to get the v by itself. And again, because we had some simplifying to do on both sides, let's distribute the multiplication across the addition and the subtraction. I'm going to get 10 minus 5v minus v on the left-hand side, 2v plus 2 on the right. Combining the like terms on the left, -5v minus v is going to give me a -6v. So I'll get 10 minus 6v is equal to 2v plus 2. Now all my simplifying is done. Let's get all my variables to one side. Again, always by subtracting. If I subtract 2v from both sides, I'll end up with just 2 on the right. And on the left, when I combine the -6v and the -2v that I got here, I'll end up with -8v. So I'll have 10 minus 8v is equal to 2. Now I have the variables only on one side, and so I can unwrap that v by reversing the order of operations. Addition and subtraction first, so subtracting 10 from both sides will give me -8v is equal to -8. And then division and multiplication. Dividing by -8 will get the v by itself, and give me v is equal to -8 divided by -8. V is equal to 1. So notice what didn't happen in this example is that the v's didn't all disappear. Right? Unlike the example in part A, we did all of our reverse order of operations, and the variable v survived that process. Right? We could always find v somewhere in our equation, all the way up until the end when v is sitting by itself. That means that this particular equation has a single solution. There's a single real number which makes this equation balance, namely the real number 1. And so this is an example of a linear equation with what we call a unique solution. There's only a single number, namely 1, which balances both sides of this equation. So two very different things happened in part A versus part B. We used the same strategy to solve each of these equations, but the results were very different because in part A, our variables disappeared. They went away, they vanished. And when that happens, that means that the equation that you get either was always true to begin with, or could never have been true to begin with. In our example, because the equation that we got, -6 equals -6, is always true, it means also that our original equation was always true to begin with, and all real numbers, w, balance the equation that we started with in part A. It's a very unusual situation. It's very rare that this happens, but when it happens, that's how you can interpret it. Part B is a bit more of a usual conventional problem. Because we didn't have all of our variables disappear, we always could find v at every step of the game. And when we got down to the v being by itself, we got the unique solution. This linear equation, v is equal to 1.